Hello, my name is Rebecca Gallivan. I'm a graduate student in material science working under Professor Julia Greer at Caltech, and I study emergent microstructural phenomena in additively manufactured nano-architected materials. Basically, I investigate how we can understand the new, cool, and unexpected properties in materials at the nanoscale. Additive manufacturing is truly enabling technology in the versatility of design and the customizability of structures. This powerful technique has catalyzed the development of numerous types of printing for a wide variety of materials. However, with these different techniques comes unique processing conditions, and as a material scientist and engineer, I know how important processing is to controlling microstructure and ultimately material properties and performance. With additive manufacturing, there is this new opportunity to push materials into unexplored microstructures and ultimately tune the knobs on microstructural design. 3D printing is also pushing us down in material design and structure to the nanoscale. In addition to being absolutely gorgeous, these nano-architectures show really unique multifunctionality in design of properties from mechanical to thermal. These unique properties are not just for design structures, but they're also found in nanomaterials. There are fundamental changes in material properties like stiffness and yield. Materials break in different ways. Something like a ceramic that might crack at the macroscopic scale can be pushed into a regime that bends and deforms like a metal. At the nanoscale, we really start to see and really start to isolate what mechanisms are behind material behavior and what defect structure and atomic processes enable material properties. What I love about my work is that I get to use this mixture of microstructure and architecture to really probe what happens when we design for the nanoscale. I'm intrigued by connecting the atomic level behavior to macro and microscopic phenomena in materials. As an experimentalist, I love that I go from printing 3D structures to imaging them in the TEM to working in the clean room, or just taking videos of these really awesome teeny tiny mechanical tests. These tests are one of the best ways that we have to investigate materials at the nanoscale. They give us a visual understanding and an ability to link that to its mechanical or in some cases other sorts of properties. And this really tells us what are the atoms doing that result in these observed or experienced material properties. In the Greer group, I get to use our awesome expertise in nanomechanics and defects to really dive into how microstructure informs performance from an atomic point of view. While inherently awesome and cool on their own, these discoveries are even more powerful in the context of applications. I love that I get to work with chemical engineers and bioengineers. I talk with people in computing and applied physics and aerospace, and I get to really think about my work and my research, not just in the context of materials, but in the context of how it intersects with a lot of different applications and devices and really a lot of different schools of thought. So really pushing forward to creatively investigate the next generation of materials, I want to use the fundamental knowledge that I have gained and I have really investigated to solve engineering problems for how we design, tailor, and control material properties to push the next wave of technology forward.